Welcome. This is 49H3 and we're going to talk about series and parallel capacitor networks. So, circuits, systems which are designed to get the appropriate potential difference across the appropriate component at the right time. That's basically what it's about. And you do this by using resistors, capacitors, inductors, little IC chips, and power supplies. And you connect them together in networks. Networks consist of loops upon loops upon loops. It's important to realize that the components are relatively inexpensive because they're mass produced, and one of the things they do is they produce not every possible value. So if you want a 17 ohm resistor, you might have to combine other resistances to get as close to 17 ohms as you can get. Same thing goes for capacitors. And so we practice working out what happens if we connect capacitors in different configurations. And there's two basic configurations to recognize. There's the so-called parallel combinations, and there's the series combinations. And just look at these two diagrams. In the series combination, if you were to take a point of interest, it would go through the first capacitor, and then it would go through the second capacitor, and then it would go through the third capacitor, and you'd have to do them in that order. Whereas in the parallel, I have a choice. I could go through the first capacitor, I could go through the second capacitor, or I could go through the third capacitor. And I'm talking about, imagine my finger moving around in there. The fact is, when you get a junction like here or like here, you have parallel branches, and otherwise you have no junction and you have a series branch. When you take three capacitors and you connect them in parallel, you'll get a different overall capacitance than if you connect the three of them in series. It matters. And the question is, we'd like to work out the equations that figure out what the value would be. Well, if we remember that our capacitance is equal to the charge per potential difference, voltage potential difference, our total charge on these, well, they're in parallel. You can imagine a whole bunch of little positive charges, and then there's a whole bunch more positive charges, and there's a whole bunch more positive charges, and they're all connected together by these wires which just connect them together. There's no effect of the wires. They're communicating bits, and so we have a lot more charges than we had on one of them. So the total charge is equal to the charge on the first plus the charge on the second plus the charge on the third. And the other thing we see is the potential difference. Because these wires are connected together, then the potential difference between those two plates is the same as the potential difference between those two plates is the same as the potential difference between those two plates, because these wires connect all these guys together at the top with the same potential, and all these guys at the bottom with the same potential. So we can say that our voltage is equal to the voltage across 1 and the voltage across 2, which equals the voltage across 3. So if we take our total voltage, total charge over our voltage, we get, well, charge 1 over the voltage plus charge 2 over the voltage plus charge 3 over the voltage, and that gives me that the capacitance in parallel is equal to the value of C1 plus the value of C2 plus the value of C3. In essence, our capacitance increases when we connect them in parallel. Over here, in series, we have a different situation. the total potential difference is equal to the potential difference across 1 plus the potential difference across 2 plus the potential difference across 3. And so we can say V total equals V1 plus V2 plus V3. Very different. And then the next thing might not be so obvious, but if I have 2 positives and 2 negatives, well, that means I must have 2 positives and 2 negatives there. And that means I must have 2 positives and 2 negatives there. Because in this piece of metal work, I've got a charge balance. And so if I took 2 of the charges and put them on the top, it's still neutral. I must have 2. If I have 2 negatives on top, I must have 2 positives on the bottom, because they combine to form atoms. So on this one, we see that Q1 is equal to Q2, which equals Q3. Whatever the charge is on this bit must equal the charge on that bit, must equal the charge on that bit. Again, dividing, we get V total over Q is equal to V1 over Q plus V2 over Q plus V3 over Q. Okay. This is upside down. So 1 over C series is equal to 1 over C1 plus 1 over C2 plus 1 over C3. You don't have to remember that logic. It's useful if you can follow it. What you can remember is that when you add capacitors in parallel, the value gets bigger. And when you add capacitors in series, the value gets smaller. So the critical things are, can you recognize a parallel combination as opposed to a series combination? And then can you remember the equation knowing that in parallel the capacitance is increase and in series the capacitance is decrease? That's what you really need to know at the moment. And if we go here, we say, what is the equivalent capacitance of a network that consists of a 3 nanofarad, a 4 nanofarad, and a 12 nanofarad connected in parallel? So I have a capacitor, I have a capacitor, I have a capacitor. There's my, I want to replace it with one new capacitor. That's what I'm doing. And I know this is a 3 nanofarad, this is a 4 nanofarad, and this is a 12 nanofarad. These are nanofarads. And what I know is they're in parallel. So for parallel, the capacitance gets bigger. So C total, let's call it C parallel, is equal to C1 plus C2 plus C3. So C parallel is equal to 3 nanofarads plus 4 nanofarads plus 12 nanofarads, which equals 12, 16, 19 nanofarads. So C parallel equals 19 nanofarads. And if you notice, the total capacitance is bigger than any individual capacitor. If we look at this next one, we say, what is the equivalent capacitance of a network that consists of a 3, a 4, and a 12 nanofarad capacitor in series? So we have the 3 nanofarad, we have the 4 nanofarad, and we have the 12 nanofarad in series. And again, I'd like to replace them by one capacitor. And what I say is C, 1 over C series is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So 1 over C series is equal to 1 over 3 plus 1 over 4 plus 1 over 12. So 1 over C series is equal to, common denominator is 12, 4 over 12 plus common denominator is 12, 3 over 12 plus 1 over 12. This equals 4 and 3 makes 7 and 1 makes 8. 8 over 12. And a whole bunch of people will give me that as the answer, because they're not thinking in terms of whole equations. I look at this and I go, oh, so CS is equal to 12 over 8, which equals 1.5 nanofarads. So also notice this is smaller than the smallest one of these. So when you add them in parallel, the answer is bigger than even the biggest individual capacitor. And when you add them in series, the answer is smaller than even the smallest individual capacitor in series. And then the next thing is, yes, you need to write in sentences. If you write in bits and bobs, you tend to make slips every now and then. And the slip you make is that you're not thinking of it as 1 over CS, you're thinking of it as CS. If all you write down is that bit, you're not reinforcing the idea that it's 1 over CS. And so that tends to show itself when you're stressed and when you're rushed. And that's during a test when your grade counts. So even though with homework you might not need to write down complete equations, it really is good practice. Last little bit. This is a bit more like it. So this is a bit of a network. It's got some parallel bits and it's got some series bits. What's the equivalent capacitance of this capacitor network? So, and these are in farads. That's a farad is a big amount. So that's 2 farads, and that's 4 farads, and that's 3 farads, and that's 12 farads. Now, what I need to do is I need to sort out, is this a series bit that's in a parallel network, or is this a parallel bit in a series network? And you know, it's hard for me to put it into words, but when I look at this, I can see that these two are unambiguously parallel. And if I could reduce them to one capacitor, then they would form an unambiguous series network. But if I try and do anything with the capacitors on the bottom with the ones at the side, it's not going to work. So what I do is I say, oh, this is parallel. C parallel is equal to C1 plus C2 because it's getting bigger. C parallel is equal to 2 plus 4, which equals 6 farads. Okay. Let's do the next bit. So I have a 6 farad capacitor, I have a 3 farad capacitor, and I have a 12 farad capacitor, but now these are in series. So I go 1 over C series equals 1 over C1 plus 1 over C2 plus 1 over C3. So 1 over C series is equal to 1 over 6 plus 1 over 3 plus 1 over 12. So 1 over CS is equal to 2 over 12 plus 4 over 12 plus 1 over 12, which equals 7 over 12. And again, a lot of people will give me that as the answer. CS is equal to 12 over 7, and 12 over 7 would be, I think, 1.7. Let me just do a quick check. 12 divided by 7, yeah, 1.7 equals 1.7 farads. Let's contrast this circuit with another circuit. So I could have a circuit where what I do is I have something like this. Can you see that this is a series bit inside a parallel? So do the series first and do the parallel second. And this guy here is a parallel bit inside a series. So do the parallel first and do the series second. Can you see the logic behind that order? If you can, you're well on your way. And if you can't, we need to work on it a bit more. Okay? There we have it.